All right, hello. Hope everyone's doing well. It's a lot of good talks this morning. This is, I think, the first time I've ever done a keynote that immediately followed a 5-minute countdown timer. So I'm pretty excited to kind of take that energy into this. I have about a half hour of material, which is relatively challenging for me because I have a tendency to talk pretty much continuously, so I'm going to get started. But this talk is all about a specific project that I've done lately that I thought was something that was fun in a sense that is, it was done specifically for the purpose of solving a problem that had kind of gotten stuck with me. So, who am I? I am Kate Temkin. I lead the more digital side of a company called GreatFET Gadgets. I do a lot of things that are designed to empower people with technology. Kind of one of my main goals is to take things that people don't easily have the ability to touch or see or kind of interact with, things like USB or things that are going over wireless protocols, and make those things that you can actually interact with, because in interacting with them, they start to become the kind of things that you can play with, and playing with them, you can understand them. So kind of my whole thing here is that every little bit of computing that we do, I think, should have a human focus at the end of it. I love doing things that directly empower people, that allow people to understand things they wouldn't, or that enable people to do things they wouldn't have been able to do, either because of the price of technology or because of some technical limitation. And so today I'm going to spend the next half hour telling you a story about a particular set of circumstances that led me from this kind of concept of deriving joy from, let me see if I can use a laser pointer on this, maybe not. Okay, so the particular example of deriving joy first from non-forbidden computing, and then this kind of journey in order to actually build a project that allowed us to extract some joy from what I'll call forbidden computing. And to understand this, I'm going to tell you a little bit of backstory. I have a particular good friend who is extremely, extremely passionate about taking her entire setup with her. One of the things she loves to be able to do is to be able to go out into the middle of nowhere with nothing other than the phone she has, and then be able to use that phone to do pretty much any computing task. And one of the things that enabled this for a very, very long time is a program called UTM, which allows you to run virtual machines on iOS and Apple devices in general. And that program was amazing because if you wanted to run something that was a Windows application or a Linux application, you could boot up a virtual machine and relatively quickly be able to access everything like you would on a full computer. So you don't have to kind of lug around a laptop, you don't have to lug around, an iPad, anything like that. You can actually do a lot of your computing directly from the palm of your hand, not remoting, just using these virtual machines. And that was a really cool technology that, in this case, sparked a lot of joy. But unfortunately, eventually, Apple updated their operating systems, iOS and iPadOS and those kind of things, in order to block the technique that was used for allowing these virtual machines to run. So we reached a point where you had a choice between either keeping a low version of iOS and not getting the newest features and security stuff, or being able to continue or being able to get those updates and not be able to use UTM. So before we get into the actual story of how we overcame those limitations, first, let's look at how this happened. How do we wind up in this situation? And in order to do that, you have to understand the backend that actually drives UTM, which is a piece of software called QEMU. And this slide, even though it's packed with text, is actually just a screenshot of the QEMU website. The most important thing is that QEMU is a piece of emulation technology that can be used for a variety of things. You may be familiar with QEMU as a virtualization front end, where it does things like emulate disks and allows you to run hypervisors like KVM or Zen. But I'm actually interested in what I think is kind of a cooler use of QEMU from my perspective, which is full system emulation, where QEMU actually emulates the entirety of a computer. And the really cool thing about that is that the computer that you're emulating does not actually need to be the same architecture as the machine you're running. So you can go and emulate a Raspberry Pi on your x86 machine, or you can emulate an x86 machine on your iPhone, which is an ARM64 processor. So this is really, really neat, especially if you want to be able to run something like full Windows on your phone. What's really cool here is the way this works. The core of QEMU used this way is an engine called TCG, which is the Tiny Code Generator. And the Tiny Code Generator is a kind of core computational translation engine that does binary translation from whatever your input is to whatever your output format is. So in this case, in the example I have on the slide, it will take x86-64 machine code and then allow you to run it on an ARM64, an ARM 64-bit processor, as we would if we were running this on an iPhone. So if we take a look at the input of some example x86-64 code, we can see the very first thing that happens is the block of computing that you want to do, represented as a bunch of machine instructions, wind up getting converted from their original representation into something called an intermediate representation. This IR, intermediate representation, is very similar to the IR that exists in compilers like LLVM. It goes from the actual things that the operations are doing to the individual kind of core abstract ideas of computation. So it's trying to break everything down to a more abstract level. So if you look on this slide, the first instruction that we had in x86 was taking register 8, XORing it with itself, which happens to translate to the intermediate representation kind of abstraction that says really what this is doing is it's taking register 8 and moving 0 into it as a 64-bit number. As we go through here, every one of the operations that was represented in x86 code gets translated to this intermediary format. And that intermediary format now has absolutely no relation to the initial platform, platform that we're emulating. Instead, it's kind of a generic way of encapsulating the behavior we want. From there, our system actually takes that intermediate representation and compiles it into an equivalent set of opcodes for the target architecture. And this process is a little bit lossy. As we go through this, we generally tend to get less efficient code out of this machine than we did coming in, but it's still code that can be run natively on your target architecture. And once you've done that translation, once you've done that binary translation, you can actually take this block of code and run it every time you would be running the equivalent x86 code. So you don't have to go and do new processing. You have native code that can run, that can do all the same things as your x86 code would have. So the whole magic that enables QEMU to work in ways that allow you to run x86 programs on your ARM64 phone is just-in-time generation, where the whole computer, your whole representation of your emulated computer, all of the execution that goes through that winds up being translated into native code, and then that native code is allowed to just run. And then once it's been translated, it just kind of stays there in a cache and can just be run over and over again without having to rerun this whole process every time we want to run that code. And this actually can be pretty darn performant. On a VM that takes about 12 seconds to boot natively, this QEMU engine can actually get that to boot in about 18 seconds using just-in-time generation. And that's not a comprehensive benchmark, but it gives you a good idea of the kind of overhead involved in those translations, which is pretty minimal. Okay, so what about using this on your phone? If you have a modern phone, you have the slight problem of that all of the code that you're able to run on that phone is usually required to be signed by a developer. And on Apple phones, every bit of code that runs should be signed by the person who actually authored it, which means that if you're generating your code just in time, if you're generating that code at the last minute in order to be able to run it as part of that Keynote process, as part of TCG, you're going to run into an issue because Apple has put protections in place preventing you from being able to have memory that you can both fill with instructions and then execute from. No memory can be both writable and executable unless you have a special entitlement that Apple doesn't give to general application developers. So essentially, if you go and try to do this on modern iOS, your just-in-time compilation or just-in-time translation is actually forbidden. So we have gotten fully into the domain of forbidden computing. Now, one obvious workaround for, I guess I shouldn't say obvious, one workaround that's obvious if you're really deep into this problem space is that you can run the whole virtual machine. You can run the processor on another virtual machine. This virtual machine being one that is a virtual machine in the type of a language VM. So we can actually take this and use it like, if you think about this as like running code on a Java virtual machine, this is very similar. There's actually an interpreter that takes all of the intermediate representation, all of the stuff that you get from that kind of QEMU processor agnostic format, and just runs it. It has a set of virtual registers, and it knows how to, it knows when it sees the intermediate representation for move 0 into register 8, it's capable of running some code that does that. Problem with that is that this is a big machine that is running in C that has these big jump tables and has all of these indirections to access a set of virtual registers. So you're actually running a emulation of a machine on your phone that then in turn runs the emulation of the machine. This level of indirection makes everything kind of get a little bit unbearable. Let me see if I can start this video properly. So this is booting ReactOS on this interpreter running on UTM on an iPhone. And one thing you might notice is that as I'm sitting here and talking, the whole system is very gradually loading things. If you run the that same reference piece of VM that I had that booted in 12 seconds native and about 18 seconds on the just-in-time runtime, on the interpreter, it took something like 90 to 120 seconds just to be able to boot up. So everything gets really unusably slow. Really, if we want this to work, we're looking for something that is ideally not painful to use, still fun to use. And that means maybe somewhere between that 18 seconds and maybe 40 or 50 seconds to boot, not something in the hundreds of seconds. So we're left in this problem space. I have this friend who has been loving running these virtual machines on her phone, but suddenly can no longer do that in the typical way because we can't run generated code. We are limited by Apple to only being able to run code that comes pre-made and that we're able to sign at the time that we're going to put that code on a phone. So this is the kind of problem space that got me thinking. So in the process of her kind of explaining that she was super bummed to lose this, we started talking a little bit about different ways around this, different ways that we potentially could start running things. And we tried running out the interpreter, and it was just too slow to be used. But there is this one kind of saving grace in all of this. which is that we can actually still run code as long as it's been pre-made, as long as it's been pre-generated. And you start thinking, well, okay, if we can run pre-made code, what if we were able to pre-generate every bit of code we might need? Now that sounds like a lot because theoretically there are infinite programs you could stick into this if you have infinite space, right? There's infinite solution space for all of these things, and to be able to capture every possible program and pre-generate code for it is impossible. But what we can do is we can take a look at the various pieces of intermediate representation that QEMU is capable of producing. So if we have an instruction like move a value from R0 to R1, or in this case from R1 to R0, we actually have a piece of AR64 code, in this case ARM 64-bit code, that does that. And so we know how to generate a single little bit of pre-made code that handles that particular case. If we were able to generate possibly a whole variety of these little tiny bits of code, these little things that we'll call gadgets, we could potentially write whole programs that way, right? But something still needs to come and stitch all of these things together, right? So if we had a pool of all of these, it would be really nice to have the ability to go and kind of thread together all the individual pieces that we have. One technique for doing that is to come up with a big list of every single gadget that corresponds to a potential thing that we might want to do. So if our program was moving X1 into X0, register 1 into register 0, and then adding register 2 and register 1, storing that result in register 0, we can find gadgets to do that, and then stitch those together by adding a little bit of code after each gadget that goes and moves its way to the next one. So we moved from a model where we were just stitching together machine code instructions to a model where we take a list that has all the different potential gadgets that we want, just kind of sitting there address after address. And then we write some code that says, let me go into this list, grab the next address, and then just jump to it. So we actually can have it so that every instruction that we want to run is followed by a really simple little epilogue that moves to the next instruction. And at this point, what we're actually doing instead of running code that we've generated is taking a whole bunch of pre-generated code and threading it together. So we need every possible gadget that you might run into for this to work. And this is very possible if you have something like 16 registers on your system, because you can go and generate add R0, R1, R2, add R0, R1, R3. You can go and actually generate code that generates every single one of these little gadgets. And so what I did is write a Python script that goes and generates the low-level assembly for every single one of the instructions that I use to implement all of the QEMU intermediate representation instructions. So here we have a whole, just a little snippet of something that is saying, okay, for example, midway through the slide, we have load a 8-bit unsigned value. And then I have a little bit of ARM code that has some placeholders. And this Python just goes through and substitutes the actual values for each individual possible argument into that template. And what we wind up with is a whole bunch of, in this case, inline assembly that implements every single possible operation in QEMU IR in AR64 code, pre-generated, all in big files that we can go and sign these and then be able to operate that kind of stitching together technique on all of these little pieces. So this kind of transitions the way that we were working on this from something that took machine code in and produced machine code out into something that took machine code in and outputs these chains of gadgets, which are then threaded together. This new technique I've chosen to call the tiny code threaded interpreter, because instead of the regular interpreter, which went and actually took that intermediate representation and ran it manually, we're actually taking pieces of machine code and stitching them together scheduling where all the jumps go so that we can actually have a continuous stream of executing instructions. So this required one last little piece, which is to implement that the actual piece that transforms from intermediate representation to those chains of gadgets, which it turns out is actually just a big collection of these opcode emission instructions, where instead of saying, let me generate the machine code for a bswap instruction, we're actually saying, let me generate a pointer, a gadget pointer in this case, let me add the address of the code that already exists that performs this operation. And what we get out is something where the intermediate representation is translated not directly to machine code, but to a collection of gadgets that then run on this new weird kind of machine that we've made, which is really a subset, a specialized subset of our ARM processor. And so what we're able to do is, just like before, we take the intermediate representation and produce something that can be run natively on our processor. And that essentially means that we're going to be outputting these long chains of gadgets, which in turn do all the same operations that we would be doing on that target processor, but with just little bits of extra code stitching everything together. So what we have is a really cool way of creating a system that is capable of running native code, just like the original was, that doesn't have to interpret things every time, but which is doing so using these generated pieces of code, which we're capable of signing at the time that we build Keynote. So all of this put together, we can finally go and actually check to see how the performance is. So what I have here is a comparison of TCI on the left, which is the basic interpreter, and on the right, TCTI, the threaded interpreter. And we can actually see how quickly these two comparatively boot. Now, you can mostly ignore when the windows change size, because that is me tapping on the screen during these recorded videos. But if you look at their content, what you will notice is that TCTI, while not the fastest thing in the world, is significantly faster than TCI, which is still figuring out how to run the desktop and do the basic rendering at the time that TCTI has been long done. And so by making a more efficient interpreter, by using this kind of cheating technique, we're able to get ourselves to something that is usable in a reasonable amount of time. So we've gone from something that was completely computationally forbidden to something that is now actually usable. And this eventually made its way into UTM, the original application at the start of this. So we've gone from something where we had a restricted computing environment where we weren't allowed to do anything just-in-time translation-like, to something where we, within those same restrictions, now have an even weirder way of doing things that still circumvents the restrictions. And on using this, we're able to run applications again and virtual machines again on Apple devices. So just to give you some statistics, I am going to preface this by saying my goal in this was not to measure performance. These are not scientific measurements. I specifically did all of this for the purpose of being able to do something that was fun and for me to implement, something that sparked joy for my friend who would no longer have to be without those virtual machines, and something that was going to satisfy the itch I had had while thinking about the problem space to actually prove that this technique works. So in our limited empirical testing, which is booting that same reference image, what we actually find is that a TCTI boot of that reference image takes about 36 seconds. So in its best, in the best case of all the trials I did, TCI, the regular interpreter, the non-hacky interpreter, was only able to make it to, I believe, like 78 seconds in its absolute most optimized form. So we basically cut the boot time in half just by doing our computational stuff in a little bit of a different way. And so this is awesome because I think this is a really great example of something where you can take a really simple problem, kind of apply that human factor, and translate it into the real thing, the real kind of outcome that I would hope to get from computing, which is that we can use this then to spark joy. And so at the end of the day, we learn a kind of extremely powerful lesson here, which is I put pithily as when life forbids you from computing, spark joy with a newer, weirder computer. But I think with a little bit of that pith removed, the real thing that I would love for everyone to take away from this and take away from all the rest of the talks, this kind of amazing gear of various neat technological excitement, is that when, at the end of the day, what you really should be doing as you build technology is thinking about ways that your work is going to make things better for people, right? The whole goal here is to focus on that human factor. And I hope this story is something that shows you just a really simple run through of my thought process when a friend of mine was feeling down because of a computational problem. So that all said, I would love to go and answer some questions from Discord. Yeah, so the things I'm seeing in the past there, like, I honestly think this graph here, which the Pithy Joy Spark graph, is something that every one of your technical projects should have somewhere in your head, so that you can at least kind of answer the question of what is this doing for me? The question from Discord is, am I going to name the debugger for this inspector gadget because it's a rad name? There actually is a built-in debugger for this that is nameless. So if you want to go into the code base and PR that, you are completely welcome to.
Hello.
How's it goes?
Oh, that was amazing. Oh, I'm so excited.
Yeah, please go ahead. Yeah, please.
So a question we got in Discord is how this technique handles immediate values. And those are either, there's one of two ways to handle that. One of them is if they're very common immediate, we build a gadget that has that immediate hard-coded. Otherwise, we put the immediate right in the instruction stream, just like you would any other machine code. So that means that what you actually wind up with is a gadget pointer, an immediate, and then a gadget pointer, and it's up to the gadget itself to go and pull that value out of that instruction stream in much the same way that a processor would do that itself in instruction decoding.
I was gonna ask. I was gonna ask about like cache characteristics and this and that and the other thing, but the actual question that I really have is, did it work? Is your friend now able to take her iPhone and do stuff like into the woods and like do stuff with it?
Yep, it's actually now fast enough to be able to be used. I'm getting blurry for some reason, but it's okay. So it's actually fast enough to be usable in. It's not as fast as it would have been otherwise, but it's definitely usable, and it has made its way into the core of that original program, UTM. So now everyone who's in this situation can do the same thing, which is kind of awesome.
That's very exciting.
They named it the very flattering UTM Slow Edition.
I'm very curious about like many parts of this. I'm not sure that like I could pick your brain on this all day, but it's not immediately clear to me that I will have all of the Bang Bang Con attendees listen to me ask question after question after question after question about like cache performance and like, wait, you could do JIT before iOS 14.4? Like, so how did that work? And all that sort of stuff. So I think we should send that over in the Discordly direction. And thank you, Kate. Thank you
Yes.
for, the thing that I liked about this was not just that it's a really cool hack, but it's important to do things for people. And I think that's the at the very beginning, you had mentioned that you can understand the world by playing with it. And this is kind of how I feel. Like here I am in my lab setup here. I have an idea for a Bang Bang Con talk next year that is exactly that, like figuring out how. Wait, I'm not going to say it out loud. The other organizers will hear it.
I won't listen.
But all the same. But by playing with objects, either physical objects or software objects, you can understand how they work, and kind of just build your mental model. I don't know. I really like that. That's
I really
that's
find
my
that,
aesthetic.
that interactivity is something that things never feel real for people until they can get their hands on them. So being able to make things tactile is such a powerful thing in computing.
I agree. Thank you very much, Kate.
Right.
Thank you for helping us close out Bang Bang Con this year.
Oh, it was awesome. Thank you so much for putting on an amazing virtual conference. Really glad to see these things kind of thriving even when we're all socially distanced. So it's been great.